couple of years ago, a fellow that goes by This Old Tony did a collaboration video with Jimmy Diresta on making a prototype knuckle duster. The subject was on prototyping, and I want to follow up on some things that I think were kind of glossed over, and add some things that may be more relevant a few years later. Since some of us makers don't have access to a machine shop, I want to show you a way a hobbyist could make something like this using resources in their apartment. Now, I'm not expecting you to go make a knuckle duster, but hopefully you could take some of the things you see here and apply them to a project that you're working on. Now, I don't know Jimmy or Tony, but I want to share how I may have tackled making this prototype if Jimmy had called on me. Rather than step through the entire design process, I'm going to just start on the mostly finished CAD. Tony did a great job explaining how he did this, so I'm just going to gloss over how I got here and recommend you go check out his video. When Tony was designing this, he was also doing something called DFM, or Design for Manufacturing. He knew he was going to be machining these parts and wanted to keep the geometry easy enough for him to work with, such as keeping these holes perpendicular to the face. I'm planning on 3D printing these parts, so I have a completely different set of limitations to work with. These holes, for instance, I can make look like a bendy straw, and it would print just fine. The reason I didn't make them look like a bendy straw is I want to have somewhat of a chance of making this machinable. The things I do have to worry about, though, are clearances and swelling. I don't know what the technical term is, but I'm just calling it swelling. So if I extrude this body 10 millimeters in CAD, it may print at 10.1 millimeters. And if I cut this cavity at 9 millimeters, it may print at 8.9 millimeters. While not a big deal for a single part, it makes for mating parts a nightmare, especially threads. So I have to take into account this swelling in CAD ahead of time and design my parts either oversized or undersized. At this point, I think the CAD is good enough to warrant a first try of probably many for a print. So I'm going to save the parts out of SolidWorks as an STL and bring them into Prusa Slicer. Here, I'm positioning them in a way that I think will print best on my printer with supports in the right places. The supports leave little bumps when finished, and I don't want them in the threads or the valve hole, nor do I really want them in a place where I can't reach them to break them out. Then I'm going to go through and add supports in what look like weak areas. I'm going to be printing this on my Elegoo Mars resin 3D printer. It was $250 delivered and about $50 for my first bottle of resin, a very low barrier of entry for a hobbyist. I also have an FDM printer, but that thing wouldn't be able to resolve the threads or keep the precision I need for most of the mating parts, nor would I really trust an FDM part to hold up to 100 psi. Now, once I'm happy with how they look, I'm going to export the body with supports as an STL and import them into Chitubox, the native slicer for my printer. Now, I'm sure you're wondering why I'm going out of my way to do this. Well, Chitubox support generation kinda sucks, and it's a lot easier to prep my print in Prusa Slicer and then bring in the ready-to-print parts into Chitubox. Then it's just a matter of lining up all the parts and hitting slice and firing up the printer. So the parts are a little tighter than I was expecting. I can't even push the valve in with an unreasonable amount of force. I'm not really surprised though. I've never really worked with O-rings before and I just shot from the hip with dimensions I thought would work. They didn't. Speaking of dimensions, the model has a valve bore diameter of 500 thou and it printed at 485. I also modeled the valve to have a diameter of 410 thou and it printed at 420 thou. So I lost about 25 thou of clearance, which must be a little bit too much for these little O-rings. I'd rather not have to reprint the body again as it was such a long print, so I'm going to try and modify the piston to account for the undersized bore. To help with that, I'm using this handy O-ring calculator I found online. You type in the O-ring you have and the dimensions of your part, and it will tell you if it's within standard O-ring tolerance. In my case, the O-ring size and bore diameter are fixed, but I can play around with the dimensions of the piston until I get something that works. The piston in this case is concentric, so just pay attention to those readings. Once I'm happy with the dimensions and think I have something that works, I can update the drawing in SolidWorks. Now, since the printer added 10 thou thickness to the model, I have to model the diameter 10 thou smaller than what I want, or 5 thou from the radius. And while I'm here, I'm going to open up the spring bore. The first spring I used was a little bit weak, so I picked up a slightly larger one. Not bad. The valve is a bit sticky, and I think I know the reason for that, but it works. And that right there, you can consider a real working prototype with all about $20 in raw material. From here, I can do a few things. I could call this prototype good enough, polish it up, and use it as is. I could head back into SolidWorks and clean up the parts and reprint them to have a better fit, or I could prep this model to be machined. That would be modeling the part with the nominal dimensions, not taking into account the swelling 3D printing has, and then sending it off to a place like 3D Hubs or Xometry to be machined. It's not as cheap as 3D printing, but it's certainly cheaper than buying the tools to make a one-off part. Also, I left a few parts out. This is everything I actually printed for this build. In the first print, nothing came out right. The valve was just wrong. The handle printed too fat and didn't fit on the hinge, and the threads for the air fitting weren't even threads. I got lazy and downloaded an air fitting off McMaster and just did a cavity to model the threads. Turns out, McMaster's model didn't even have threads, but it was just triangles revolved around a tapered cylinder. You saw the revisions after that, but keep in mind prototyping like this is an iterative process and you should expect to go through a few iterations. Good luck and happy making.